This is section 7.5 on the topic of dot product. The idea here is that, as you saw in the last section, we've learned to add and subtract vectors. We've learned how to multiply a vector by a scalar. We've learned what those operations mean, both in terms of the component form of a vector, where you write out the components in vector brackets, or in terms of I and j. And we've also seen what that means graphically to add or subtract or take a scalar multiple of a vector. But what we did not see so far is how to take two vectors and multiply them together. And the reason for that is that there's different ways you could define multiplication of two vectors that are useful in different situations, different applications or contexts. So what we're going to see here today is, or in this video, is one type of product called the dot product between vectors, and we'll see some applications of that type of product. There's also other ways you can multiply vectors. We're not going to learn about those here. We're learning about this very specific way of multiplying vectors, defined to be something we call the dot product. So here we have a definition. We'll see why this is a useful definition, but for now we're just going to try to see what this is saying. The definition of a dot product is that if you have a vector v equal to, or having components a1 and b1, and a vector w having components a2 and b2, their dot product is defined as v dot w. And I want to emphasize, since there are other types of products between vectors, you must write the dot here. Right? You don't want to write just like VW. You don't want to do that. You want to write V dot W. So that dot indicates that we're doing a very specific type of multiplication here, defined in this way, so that V dot W is A1 times A2, so the product of the first two components, plus B1 times B2, the product of the second two components. So that's a pretty simple operation to compute, but notice here, the dot product results in a scalar value, just a number at the end, not a vector value. So you take two vectors v and w, their dot product, once you compute it, is just a number, just this scalar out here, a1 times a2 plus b1 times b2. Let's see this in these first few examples. Let me jump in here. V dot w, in this case, is negative 2, 2, dotted with 3, 14. Well, what does that make? We're saying multiply first component times first component plus second times second. Right? So it's multiplication component-wise and then add the results. So this is negative 6 plus 28 is positive 22. So I'll write my answer maybe back up here. V dot W equals 22. Another note on notation here. Remember that when we type vectors on a computer, we can use boldface for the boldface font for the letters representing these vectors, the V and the W here. If we're writing these things by hand, though, since it's hard to show bold text when writing by hand, you do want to put these little vector hats that I've written on top of my vectors. Just to denote those are vector values, those are not scalar values. But notice at the end of the day, when we dotted these two vector values, we did get a scalar value. A dot product produces a scalar value. You might even hear this called a scalar product occasionally. Let's look at, well, maybe actually take a beat here. Pause the video if you like and go ahead and try part B and C, where you're dotting V with itself and W with itself. Hopefully you've had a chance to pause if you wanted to do that. I'm going to jump in here and actually complete these. V dot V is just this vector dotted with itself. Right. You don't want to call this V squared. Right, we are multiplying it with itself, but this very particular type of product, this dot product, we typically don't use powers to represent, so don't call it V squared. We don't want to do that. Okay. Instead, we'll just write v dot v, not v squared. V dot v equals negative 2 times negative 2, which is positive 4, plus 2 times 2, which is another positive 4. So we get 8 here. I'll run through this second one real quick, and then I want to see something about these results that might be interesting or useful. 314 dotted with 314, that's W with itself. First component's 3 times 3 gives me 9. Second component's 14 times 14. Can we do that math? What is 14 times 14? Let's see. I think it's 196. Which is 205, looks like. Right, so W dot W equals 205. Again, a scalar value. And keep in mind, at this point, we have no idea, or we haven't discussed any idea about what these numbers we're getting out of these dot products represent. And that's fine. For now, we just want to make sure we can actually compute these things. But let's take a beat here and figure out, I want to make a connection here before we go much further. Let's look at parts B and C where we dotted a vector with itself. Let's on the side here compute the magnitude of V. Remember, the magnitude is the root of the sum of the squares of these components of V. So negative 2 squared plus 2 squared. Looks like we get root 8. And I'll just leave that in that form. If I go over here to part C and do the same thing with W, look at its magnitude. What do I get? The root of the sum of the squares of these components. Which is root of 9 plus 196, root 205. So let's see something already. When we dot a vector with itself, it looks like we're getting the same thing we would get inside the root when we take a magnitude of the vector. Right? Same here. When I dotted W with itself, I ended up with 205, which is what I have inside the root in the magnitude of the vector. This is not a coincidence. It turns out in general, this is true. When we dot a vector with itself, this is another way of writing its magnitude squared. Right? If I square it here and here and here, I just have 8, which is the same as my dot product. If I square the magnitude of W here and here and here, I just have 205. Oops, 205. Which again is just the size of the dot product. So the magnitude squared equals the dot product. This is a nice, easy way to get the length of a vector, or even to express it in terms of these dot product operations. So let's go a little bit further here. Let's talk about some of the properties of dot products. If U, V, and W are vectors, and C is some scalar, just a number, then all of these rules here hold. The first rule here is telling you that it doesn't matter which order you dot two vectors in. V dot W is the same as W dot V. The second one here is saying that if I have a scalar multiple of a vector V, and I want to take that scalar multiple and multiply it on another vector W, I can actually pull the scalar out front and just dot the vector parts, then multiply that scalar on out at the end. Right? A scalar multiple in a dot product says the scalar can come out front and wait for the vectors to dot and then be multiplied back in at the end of the day. 3 here is telling us that dot products actually distribute across sums. V dotted with the quantity W plus U is V dot W plus V dot U. Right? It distributes. This actually tells us that we can, distribution is all we need to say that we can FOIL vector binomials. For example, V plus, I'm running out of letters here. I don't know why I'm not able to think of a good vector. Let's just call it X. V plus X dotted with W plus U. You can actually just FOIL this out. It's V dot W plus x dot w. I actually did inner, I guess, instead of outer. Plus v dot u plus x dot u. Right? Distribution, this property 3 here, gives us the ability to FOIL vectors in this way. It's a nice fact. 4 is exactly what we saw in the previous example, that when you dot a vector v with itself, you actually just get the magnitude squared of that vector. 5 is saying that if you dot v with the 0 vector, any vector v dotted with the 0 vector, just the vector of all 0 components, equals the 0 scalar, which should make sense. All those zeros here are going to hit all those components of v, making everything add to 0. And here, this one I would say is pretty similar to what property 2 was saying, but it's saying really that scalar, not only can it be put outside of a dot product, but it can instead be put to the other vector first before dotting. So really it's saying a scalar can go to any part of a dot product. It can go to the v or the w or outside of the v dot w. Just some nice little properties there. It's going to help you be able to work with these things more easily. So let's see, why do we care about dot products so much? We saw it's kind of useful for expressing magnitude somehow. But this, I'd say, is definitely more useful, is the fact that we can find angles between the tails of two vectors using a dot product. Right? If we can express an angle just doing addition and multiplication, what's involved in the dot product, that's a pretty powerful tool. So let's see here. It says given two vectors v and w in standard position, meaning tail at the origin, the angle theta between the tails of v and w is the angle formed by these two line segments here. Right. So if we think of this angle between our two vectors v and w, we can actually say that so long as these are non-zero vectors, so there is actually an angle there, these aren't just trivial vectors, cosine of theta equals v dot w over magnitude v magnitude w. Using a little inverse trig, we can say that leads to this other fact, that theta itself is cosine inverse of the dot product of v and w over the product of their magnitudes. This is a huge leap, so I actually want to see how we can see that this is true. To prove this, we typically actually use law of cosines on this triangle over here. Right? This isn't too bad. Let's use law of cosines here. Law of cosines says that v minus w, the length of that squared, right? So that's our red length here. The length of that side of our triangle should be the sum of the squares of the other two sides. Right? The magnitudes I'm writing here just mean the length of these vectors, so the length of these sides of our triangle, the length of v, w, and v minus w. And if you remember, there's this little correction factor we have to include here. This is minus 2 times, this is law of cosines, 2 times magnitude w, magnitude v, cosine of the angle between them. Right, cosine of this angle theta. This is just law of cosines, but what's useful here is now rewriting each of these, on this side of, at least, rewriting each of these, or rewriting this magnitude squared as v minus w dotted with itself, like we saw we could do from our vector properties. Dotting a vector with itself gives us the magnitude of the vector squared. So I'm going to start on this side of the equation and see if I can make the other side of the equation, or see what I can do to manipulate with the other side of the equation. Leaving this side alone for now. That's my point. Okay. Well, we said we could distribute or we could FOIL something like a binomial in two vectors dotted together. We just very carefully FOIL. V times V is first times first. Outer times outer is V dot negative W. Inner times inner is negative w dot v, and last times last is negative w dot negative w. On the right side, we still have the same old expression. Takes a while to write all those magnitudes. Often you'll see it where the magnitude is expressed just like an absolute value with just a single bar on either side. I'll try to match your book's notation here though and use 2. So what do we have from here? Well, notice what's happening. V dot v, that's magnitude v squared. Again, by that same vector property that let us rewrite the original magnitude squared as this thing dotted with itself. Well, now we have v dotted with itself, so that's v squared in magnitude. And here, this is just a negative 1 multiplied on w. Right? And we know a scalar involved in a dot product can come out to the front of the dot product. Same thing with this piece. Same thing with both of these pieces. Negative and negative will make a positive w dot w, which is magnitude w squared. And on this side, what do we have? Same old stuff. Lot to write out. Yikes. Okay. Now let's check out what's happening here. Here we are dotting 2 vectors, v and w, just in opposite orders. But we saw that the order we dot these in does not matter. So these are actually the same thing. Negative 1 copies minus another copy, that's just negative 2 copies of v dot w. Right, to contain both of these two. And notice what's left, the magnitude v squared. I have a copy of that. Oops, left off my square. I have a copy of that on both sides. Subtract that from both sides and it cancels. Same with the magnitude w squared. I have a copy on both sides. Subtract it and it cancels. So all we have is negative 2 v dot w equals negative 2 magnitude w magnitude v cosine of the angle between them. Divide off the negative 2 from both sides, and we have our result. V dot w is all that remains on this side. Let's divide these magnitudes over, which we can do because we're assuming that neither of these magnitudes is 0, right? Because these are both non-zero vectors up here. So their magnitudes are not 0. We can divide them over to the other side. Doesn't matter which order I write. A multiplication of 2 magnitudes. But we get our result. Right? So law of cosines, I think this is one of the great applications of law of cosines. It lets you break apart this vector picture and get a very powerful statement about dot products. Right? We want to know that anytime I want the angle between 2 vectors, I can do it if I use some cosine inverse stuff and a dot product. Okay, so we'll remember this is a very important fact. Let's try an example. Let's find the angle between these 2 vectors. Let's round to the nearest 1/10 of a degree. So all we need to do is remember theta equals cosine inverse of v dot w over the product of their magnitudes. Right? So what is this? Cosine inverse of, let's work out these pieces. V dot w down here, easy enough. Remember this vector and this vector, that ij expression is the same as this for v, and this 3, 4 for w. This ij notation for these vectors up here is just exactly the same as writing in vector brackets this way. Here you're writing this as a sum of 2 kind of constituent parts of the plane, the I vector and the j vector. Any other vector is just a combination of those. Here, instead of writing it as a combination of I and j, we're just writing how far in the x and how far in the I and the y direction do you travel from the origin to get from the initial determinant points of your vector. So this is what we have for the dot product here. We compute this out. Negative 2 times 3 is negative 6. 3 times 4 is 12. Add those results, we get 6. We need the magnitude of each vector. Remember, magnitude of v, you can think of taking, you could say the magnitude squared is v dotted with itself, or you can just remember it's the root of the sum of the squares of the components v. So it's root 13. V, it looks like, is 3 squared plus 4 squared inside the root is 9 plus 16 is root 25. Well, that one's nice. We get 5 out of that. So we've got all the pieces. The dot product 6, magnitude v is 13, magnitude w is 5. Let's put it all together. Cosine inverse of v dot w is 6, magnitude v is root 13, and magnitude w is 5. So this is the value. Cosine inverse of this number is our angle. Let's go ahead and plug this into a calculator. We're told to round to the nearest tenth of a degree. 6 divided by 5 square roots of 13. Be careful with parentheses here. I get 70.6 degrees roughly. Let's see if this is believable by drawing a quick little picture here. Kind of tilted my coordinate system. That's okay, so though. This vector v, I'll go ahead and plot that. That's at negative 2, 3. I'll plot that in standard position. That's a vector sort of like this. Goes from in standard position, it goes from the origin out to here. The other vector 3, 4 goes out 3 and goes up 4. So a little higher than this guy. So let me draw this better. Let's get a real picture going here. Okay. Let's say that's roughly the vector v is pointing. Negative 2 in the x, 3 in the y. And the other vector, 3, 4, should be roughly here, I'd say. That's about right. And notice that looks pretty close to a 90-degree angle, but a little bit short of that, right? So it would be believable that this angle is 70.6 degrees. Okay. VW. It's believable. You always want to check your results for reasonableness, and this one looks reasonable. Okay. So let's look a little bit further here. We're talking here about how to kind of interpret the dot product, what we're getting out of its value. And we're going from this fact we saw before that cosine of theta is v dot w over magnitude v magnitude w. Well, by multiplying, we actually saw this above, we can rewrite this in this form. V dot w it's really just the product of their magnitudes times cosine of the angle between them. Now notice, if this dot product is positive, it means the cosine part had to be positive because the magnitudes aren't going to make this stuff negative, right? The magnitudes are always positive. Only the cosine could flip all the signs here, all the positive negative sign here, and make it a negative quantity that the dot product equals. So if the dot product is positive or negative, really depends on this cosine factor. If the dot product is positive, that means the cosine factor was positive. And we remember that cosine is positive in the first quadrant, 0 to 90 degrees. If this dot product comes out, so that would mean the angles have an acute angle between their tails. The vectors have acute angles between their tails. If v dot w is less than 0, then cosine's negative, right? This cosine is negative, meaning our angle must be between 90 degrees, the positive z-axis, or the positive y-axis, and 180 degrees, the negative x-axis. So quadrant 2. Right? So that would be the case where we have an obtuse angle between the tails of our vectors. You might say, well, what about these quadrants down here, 3 and 4? Well, keep in mind, we're talking about the tails of two vectors. We're always thinking of the smaller angle between those, not the angle all the way around. There's always, no matter what vector, non-zero vectors we have, if we draw them tail to tail, there's always this smallest angle between them, and that'll be less than pi. So we're only going to look from 0 to pi when we consider these angles. Right, if I have something right about at pi minus a little bit, epsilon, then I can take that angle. If I go a little bit bigger, and it's out here, well, instead I can just take this angle and it'll be less than pi. Right, so no matter what my vectors are, non-zero vectors, I can take this angle to be between 0 and 180. If it's between 0 and 90, it means there's an acute angle between the tails of our vectors. If it's between 90 and 180, that means it's an obtuse angle. Well, those directly control the sign, the positive, negative sign of the dot product. V dot W is positive, means acute. Vectors are overall in the same kind of direction. V dot W is negative, means they're obtuse. Overall, they're kind of in opposing directions. Now, if the dot product is 0, they're neither acute nor obtuse. That means cosine would have to be 0, right? Because neither of these magnitudes are 0. So if this side's 0, it must be because of the cosine factor. So if the dot product is 0, the cosine of theta must be 0, which means we have a 90-degree angle. In this case, we say the vectors are orthogonal. Orthogonal. Something like this. That's a pair of orthogonal vectors. And so from this fact that that's what we have to have in the dot product to get these to get this 90-degree angle, we get this fact that two orthogonal vectors are orthogonal if and only if their dot product is 0. This is a great way to test if you have a right angle between two vectors. It's a way to test for a right angle. Just take the dot product of your vectors. If it's 0, you have a right angle between them. Now, on the other hand, we could think of, let me erase some of this mess up here. On the other hand, you could think of what would happen if you have two parallel vectors. Oops, that doesn't look parallel. Technically, I would say, let me fix this. Technically, I would say vectors like this and this guy down here, I would say these look parallel to me. I would say something that looks like kind of the same direction but opposite, something like this and this. I would call this anti-parallel, but I think your book just calls this parallel as well. So we're going to assume both of these count as parallel. Okay. So let's see what's happening in each of these cases. In each of these cases, if I put our vectors tail to tail, so for example, the first case here, if I put these tail to tail, they'd overlap, right? I'd have one vector on top of the other. That would mean the angle between these tails is 0, right? There is no angle between them. Well, if the angle is 0, then cosine of 0 is 1, and the dot product must just be the product of the magnitudes because the cosine is 1. Right? So the vectors are parallel. That means you're going to get the dot product is just the product of their magnitudes, at least from this first case that we looked at. In the case of what I called anti-parallel, but your book still just counts as parallel, If we put these tail to tail, then the angle between them is pi. It's like a straight line. And if I put pi into here, into this cosine, cosine of pi is -1, so V dot W would be -1 times the product of the magnitudes. V dot W would be -1 times the product of the magnitudes. Right, so you can learn a lot about how these vectors are related to each other just by taking their dot product. Okay, let's look here. Let's determine if the given vectors are orthogonal, parallel, or neither. This is pretty easy. All of these questions relate to a dot product, so I'm going to dot these two vectors, k and s. When I do this, I'm taking first times first, plus second times second. Right. So if you compute this, let's see what we get. 1.8 times -0.9, that's -1.62. 0.3 times -1.5, that's -0.45. Right. So let's see, when we put these together, I get -2.07. Notice that is not 0, which means these are not orthogonal. They're not forming a right angle. So to see if they're parallel, we need to see if the product of their magnitudes, right? Let's scroll back up. We need to see if the product of their magnitudes, magnitude V, magnitude W, if that is positive or negative of the dot product, if it's 2.07 in this case. So we need these magnitudes individually. I'll compute these very quickly. There's other ways to do this to figure out if two vectors are parallel. You can think as one a scalar multiple of the other. That would be parallel. Maybe you can guess here, but I'm going to compute this out and see what we get. 1.8 squared plus 0.3 squared. I get that this is the root of 3.33. And when I compute the magnitude of S, that's -9 squared plus -1.5 squared. When I do this on a calculator, I get 81 plus 1.5 squared. I get 83.25 inside the root. So when I multiply these together, I get root 3.33. I haven't rounded anything yet. Times root 83.25. Where we can combine this into a single root. Yeah, combine this into a single root. Maybe you can already see the punchline, but I'm going to continue through the calculation. This is root of 277.2225, which when I take the actual square root, I get I get actually an exact value, 16.65. So let me make sure I calculate everything correctly. Oh, I don't think I did. Let me go back and calculate my dot product again. I think I did something incorrect here. 1.8 times -9, that's not -1.62. Let me redo this. 1.8 times -9, it's -16.2. Ah. And so if we put this together, we're seeing something pretty important coming out here. -16.2 plus -0.45 Look what we have. I was wrong. Check your work on these. What do we have? We have negative 16.65. So we are seeing the magnitude of the vectors, the individual vectors multiplied together, does equal negative of the dot product. Negative. Okay. Yes. So it looks like, yes, these are parallel. I would say these are anti-parallel because we have the negative out front. But yes, these are parallel as your book considers it. I would say K is parallel to S. Okay. I took quite a bit of space on that one. On the next ones, I'll go through it a little more quickly. Maybe pause here, see if you can do problems 4 and 5. But I'm going to go ahead and jump in. So pause if you don't want to see the solution quite yet. So let me look at problem 4. Again, I'm going to start with the dot product. Dot these two vectors. I think the bracket notation is a little easier to work with. Many people disagree with that, so use whatever you like. Well, 2/3 of 15, that's 10. Negative 12 times 5/6, that's negative 10. This equals 0. Right away we get orthogonality. Went way quicker. Sometimes when we want to say B is orthogonal to A, we'll use this notation. This means orthogonal. Just like this symbol over here meant parallel. Okay, so not too bad there. That one went quick. Dot the vectors, we got 0. That means orthogonal. Here when we dot R and S, problem 5 here, we get negative 30 plus negative 30. That's negative 60. You might say, oh, that looked like it was going to cancel, but it didn't quite cancel. Right. So we know this is not orthogonal. We have to determine whether we have parallel vectors. So let's see this one a different way. If parallel, there must be a scalar C so that one vector multiplied by C equals the other vector. Right? That's another way of thinking what parallel means. One is just a scalar multiple of the other. Has the same direction but possibly different length. Well, so what does that say? If C times R equals S, that means C times negative 615 equals 5 negative 2. If we can find a scalar C that satisfies this equation, it means our vectors are parallel. So let's see, this would say that absorbing that scalar into the vector on the left would tell us this equation must be true. And we know for this to be true, each component on either side of the equation must be equal. Negative 6C must be 5. 15C must be negative 2. Well, now you're just seeing, can these equations here be solved? This one gives us 6 equals, this is a system, they're not two separate equations. It's a system of equations. C equals negative 5/6. Plug that into the other equation and see if it satisfies it. This is equation 1, this is equation 2. Equation 1 tells us C equals negative 5/6. From 2, that would say 15 times negative 5/6 equals 2. Is that correct? Negative 2. I'll cancel a 3 here. And here we get negative 25 equals negative 25 halves equals negative 2. That is not true. The solution to this equation does not match this one. There is no solution. No C exists so that this is true, so that one vector is a scalar multiple of the other. These are not parallel. And they're not orthogonal. Slip that in there at the end. My work's kind of a mess on that one. Sorry about that. But that's our answer. Not parallel and not orthogonal. They just point in some other directions versus each other, compared to each other. So I think this is one of the great applications of dot product and vectors, decomposing into two orthogonal vectors. The idea here, we'll come back to these pictures, but the idea here, I want to explain down in this blank space. The idea here is, if I give you a vector v, well, we know in our usual coordinate system, the components of this vector are just, let's say the components are a, b. The components tell us how far we go in the I direction and how far we go in the j direction, so that this vector in the j direction and this vector in the I direction, so that bj plus ia, let me write that in the right order, ai plus bj, when you add this vector and this vector, you get back our v vector, right? By graphically adding b and a, right, putting them tail to tail, thinking of the parallelogram they form, the diagonal is this vector v. Right, so when we write v in this way, we're really writing it as a units, let's say it this way, v is a times vector, let's say it this way, a units in the direction of I, and b units perpendicular to that direction. I.e. in the direction of j. That's what this is really saying, is that the components of our vector naturally describe how far we go in the direction of the I vector, just some direction given by the positive x-axis, and how far we need to go perpendicular to that, the j direction, to get these two vectors that add up to v. How far do we go here and here to get v? Right, this long vector I've drawn here would be ai. The long vector I've drawn here would be bj. So that's bj2. A plus bj gives you v. Okay. My picture's a mess now. Oops. There's my v vector. So what I'm getting at is that there's really nothing special about this direction of I. We can actually do this with any number of vectors. We could take any vector. The idea of what we're doing here is take any vector, v equals ab, and decompose it, rewrite it. I would say this vector v in usual notation is decomposed into some part I plus some part j. We want to decompose a little bit differently. We want to decompose into a vector v1 along the direction of a given vector w. Instead of along the direction of I, which is arbitrary, how do we do this for any vector? How do we break it up into some part, some v1 vector in the direction of w, plus a v2 vector perpendicular to w? Right? It's exactly what we do up here when we talk about our ai plus bj form of this vector v. It's exactly what we're doing. We're just saying that that w vector I'm describing down here would be like the I vector. But it doesn't have to be. We want to do this in a more general setting where it's not just the I and the j that we decompose into, We want to choose any direction. So given a v, maybe here's the direction of w I want to work with. So I'm thinking of putting this is my w vector, this is my v vector. We want to take this vector v and break it up into two vectors, one in the direction of w and one perpendicular to w, so that when you add these little guys, you get back this v vector. Right. That's the idea here of decomposing these into two orthogonal vectors. So let's see. We've got formulas for how this is going to work out. We call, let me break this down a little bit more. Up here, and the picture's already given, we call the vector projection of v onto w. It's given by this formula. We'll see where that comes from, but this is the picture we're thinking of. Right? We have this v vector. We have this v vector up here in black. And we're given some other direction w, some other vector from A out in this direction. That's our w vector. From A all the way out here in black. From here all the way to here. It's a long vector as drawn. And what we're doing is figuring out how can we decompose this v vector into some vector that's in the direction of w plus some vector v2 that is perpendicular to w. Well, this v1, the part that's in the direction of w, we call that the projection of our original vector onto this w direction. Right? This is the projection of v onto w. And I want to see a little bit about why we get this complicated formula for that v1 vector. So let's go back down here and see where that comes from. So erase some space here. Let's see where this comes from. So the way I think about this is take your v vector and your w vector, place them tail to tail. That's that v1 vector called the projection of v onto w. And this is the v2 vector perpendicular, so that when you add v1 and v2, you get back your original vector v. So we want to figure out that formula for the projection of v onto w. Well, the way I think about this is we usually call the angle between two vectors v and w. Let's call the angle between those two vectors, it's all just one vector there. Let's call the angle between those theta, as usual. Then we can actually figure out what length this vector should have. Right? This length from here, from the common tail here, out to where this perpendicular drops down, that length should be the magnitude of v. We know the magnitude of v1, the projection, I should say. The magnitude there should be, well, let's see if we can figure this out. Well, this vector is v, so the length of that hypotenuse is magnitude v. It looks like it should be magnitude v times cosine of theta. That'll give me this adjacent length here. Great. So that's our magnitude. We can rewrite this cosine using some dot product formulas. Cosine of theta, let's remember, is when theta is the angle between vectors w and v, it's v dot w over magnitude of what we're projecting on, of the product of the magnitudes of the two vectors. So we can replace this cosine theta here with this expression. Oops, I'm forgetting my double bars for magnitude. And that gives me the existing magnitude v outside, then this expression. Keep in mind, I'm only finding the length of this thing so far. We are going to need to figure out the vector that has this length in the right direction. But for now, let's do this. V dot W, that's a scalar. Both these magnitudes down here, those are scalars. This is a scalar. We can cancel that magnitude V. So finally, we get that the length of V1, which is just the projection vector of V on the direction of W, we get that that is V dot W over magnitude W. Sometimes you'll hear this called the scalar component of V in the direction of W. I don't think our book uses that language though. So let's go a little bit further. We found the right length, but how do we get a vector in the correct direction with that length? Well, let's figure it out. Let's find a unit vector in the right direction. So in the direction of W. So that V1 equals the correct magnitude times that unit vector that doesn't bring any extra magnitude with it because its length is 1. We just take the right magnitude, the right length, scalar length we need, and multiply it onto a unit vector in the correct direction. Well, the correct direction is the direction of W, right? The direction of W is the direction we want this projection vector to be in. But we know how to find the unit vector in the direction of a given vector. We take the vector and divide by its own magnitude. We called that normalizing in a previous lecture. This thing is its own magnitude times a unit vector in its direction, which is its own magnitude times the unit vector here. We'll just plug in now. So what do we have at the end of the day? We have that our vector we're looking for, this vector projection, is really just W over magnitude W times the length of the vector we're looking for. But we already worked out the length. That was up here. So I think of this as, here's all our length for this projection vector. Then we multiply it by a unit vector in the correct direction. So it's like we've separated out direction and length separately. Well, then we can actually put these two together, these magnitude W's. And I think this is the formula we saw above. We'll double check. Right, because all this is scalar stuff. I'll keep that all together here. And there's our actual vector. Right, so sum it up. The projection of V onto the direction W is V dot W over the magnitude of W squared. Forgot my square from combining. W squared times that vector W. Let's see, is that the correct formula? V dot W over magnitude W squared times the vector W. This is good. So that gives us this guy. And remember, we said down here that the whole idea is that these V1 and V2, the parallel vector and the perpendicular vector to W, should add to produce V again, right? Well, that means if I already know, right, this projection vector, that's V1. If I already know V1, I can solve for V2 in terms of V and V1. That's what we did here. V2 is just V minus V1. Sometimes you'll hear this piece called the V2, you'll hear it called the orthogonal projection of V onto W. But it just equals V minus V1, which is the projection vector. There's your formula. So we have formulas for these things. I know this video is getting long. I think we're right at the end here. Yeah, we've got 2 problems left. Let's go ahead and finish this up rather than breaking into a new video. Feel free to pause often. I can't stress that enough. Pause, take notes, take a breather, get a drink of water, watch a movie, come back. But take breaks often. I don't want you to burn out on these videos too much. Let's find the projection of V in the direction of W for these given vectors up here. Right, this is easy. We're just plugging into a formula. V onto W is V dot W over magnitude W squared. That's the scalar part. The vector part is W itself multiplied on that scalar. So let's compute the parts. V dot W is just 3, -1, dotted with -8, -3. So -24 plus 3 is -21. Check my math there. Well, we want W squared. Remember, that's just W dotted with itself. So maybe that's another way to remember this formula. V dotted with W over W dotted with W. That's really what we have there. That's maybe a better way to think of it. But anyway, so that W squared in magnitude is itself dotted with itself, which is -8 squared plus -3 squared. Looks like that's what we get. So let's put it together. The projection of V onto W equals V dot W, which was -21, over W dot W, magnitude of W squared, in other words, which is 73, times vector W. Vector W itself was -8, -3. Right. You could leave it just like that. That's perfectly fine for a final answer. If you wanted to sort of factor a negative out of here, you could just call this 21/73, 8,3. Okay. Let's see. Maybe we'll try to visualize this after we finish the next part. Let's find vectors v1 and v2 such that v1 is parallel to W and v2 is orthogonal to W, and the two vectors v1 and v2 add back to V, to this V we had up here. This is exactly the decomposition problem. We're decomposing this V vector, 3, -1 up here, into something in the direction of W plus something perpendicular, orthogonal to W. So we actually already have part of this puzzle, right? If I'm drawing a vector V, I have another vector W. We're trying to break it into this vector V1 and this vector V2 so that V1 plus V2 equals W. But we've already found V1. V1 is just the projection of this vector V onto the direction of W. We already found that in the previous part. That's 21/73 times the vector 8,3. It's that scalar multiple of 8,3. And we know how to figure out this other piece, the V2. We got V1. To find V2, we just play with this equation. Oops, sorry, this shouldn't equal W, it should equal V. Just subtract the V1 over. So it's the V we started with. If you remember, the V that we started with is this vector 3, -1. (3, -1). And all we're going to do, that's our 3, -1, subtract off V1. Subtract off that projection vector we found. And we get this. So really, when we have this vector minus this vector, that's a new vector, 3 minus the scalar times 8. Probably shouldn't use a dot there, just to be careful. And -1 minus the scalar times 3. Okay. So let me do this calculation real quick. Let's see what we get. Let me pause and come back. Okay, I calculated these. It looks like the first component comes out to 51/73, and the second component comes out to -136/73. So you could write this as 1/73 times this vector. That should do it. Right, that'll work. That's our v2 vector, so that's this vector here. Right, maybe it's a good idea to visualize, I don't know, maybe not. These numbers aren't nice enough. But all we're doing is working out the projection of one vector onto another. And so I think it's important to know if I draw two vectors, how do I actually work out what would look like the projection of one onto the other? Well, first step is take these two vectors, redraw them tail to tail. Don't rotate them. Just redraw them. There's my W redrawn. Maybe that's a little off. That look roughly parallel and the same length. I'll do the same thing with V, roughly parallel to the other V in the same length. So I want to redraw them tail to tail, and whatever you're projecting onto, right? We have the projection of V onto W in our formulas. Whatever you're projecting onto, the W in this case, think of drawing the dotted line through that vector. So maybe my V will be here. I'll cheat. That'll be okay. So draw that dotted line through the vector you're projecting onto, and then drop a perpendicular from the tip of V down onto that dotted line. That's how we're going to draw these. That's a general method. Then this vector from their common tail where you started out to that perpendicular mark, that's your projection of V onto W. And the vector from where you left off there back up to the tip of V, that is your V2, or your orthogonal projection of V onto W. I say this in a very general way because notice how this picture is a little different than the other ones we've seen. That's because their angle between their tails is greater than 90 degrees. In that case, this projection actually points in the opposite direction as W, and that's just because there's a dot product that turns out negative in this projection formula, and that theta is bigger than 90. Right? So maybe interesting to do with these two before we end is to project in the other direction. Let's project W onto V and see what that would look like. So W onto the direction of V, let me again redraw these tail to tail. There's my W. There's my V. Thanks. I'm running out of room. Make some room. Making some room here. There's my W vector. I'll say V looks roughly like this. That's not perfect. That's the best I can do right now. We're going to project V onto the direction, W onto the direction of V. So now we put the dotted line through V and drop the tip of this guy perpendicularly down to that line. Our projection vector goes from the common tail out to that perpendicular mark. And the orthogonal projection, the V2 vector, goes from this common tail out to the tip of V. That's the V2 orthogonal projection of W onto V. Right, a great practice for this sort of drawing problem, which I like to put on quizzes, is to draw yourself two vectors, I don't know, in any given direction. That one's not great. Just draw some vectors and see if you can draw out these pictures, the projection pictures, for any pair of them. It's great practice. It'll really get, and do it in both orders, V onto W and W onto V. It's really great practice for this stuff. Okay, that's plenty long for this section. We will pick up with the next section in the next video.